Now we're going to look at the constant multiplier rule and the sum and difference rule. Now, these are arithmetic combinations. It's still the same basic derivative rules. We've looked at chain rule, which just was the same basic derivative rules, only on more complicated functions. The same here, more rules, except they're just combinations of the original rules that you had. So this function f of t is 2 times t to the third, so 2 is a constant multiplier, minus t to the fifth, plus e to the 2t, minus 4 times t, another constant multiplier, plus 5. The 2t, 2 times t is a constant multiplier. The basic rules are all based back on slopes. Derivative is a rate of change. It's based on a slope. So everything that we do with all these rules can be proven. We're just looking at what the results are. So let's use the rules and take the derivative, and we'll see how the rules go. If I want f prime of t, the constant multiplier rule tells us that if you have a constant times a function, the constant stays constant. So I have 2 times, and then I take the derivative of t to the third. That uses the power rule. I get 3t squared, minus t to the fifth, uses the power rule, 5t to the fourth, plus e to the 2t. Well, this is not just e to the t, which was one of the basic derivative rules, but the 2t up there means we also have to use a chain rule. So to take the derivative of e to the 2t, the outside function is the e to a power. It repeats itself. And then you multiply by the derivative of the exponent. The derivative of 2t is 2. Minus the derivative of 4t is 4. And the derivative of 5 is 0. So when I have my 2 times 3 to the t squared, 3 times t squared, I get 6t squared, minus 5t to the fourth, plus, and a lot of times we write the 2 in front of the e to the 2t, and then minus 4. So this is considered about the simplest form. And notice that with the constant multiplier, I could have just brought the 3 around front times the 2 to get 6 in one step. So you can do that with your constant multiplier. Let's look at a function that's a little more complicated, but does involve sums and differences within something we've already done. Let's look at the function f of x equals x cubed plus 3x, but to the 5th power. So my sum is inside another function and not just a sum or difference as part of the function. Here I have an outside function that's a 5th power and an inside function that is a sum. So to take the derivative of the outside, 5, the inside stays, but it's now to the 4th power. So my outer derivative was 5 something to the 4th. The sum on the inside becomes part of the derivative of the inside using the chain rule. Derivative of x cubed is 3x squared, plus the derivative of 3x is 3. So I've used basic rules and the new sum rule. And with the 3, you can either consider that the basic rule of m times x, slope of a line, or the constant 3 times x to the first. Derivative of x is 1. Let's move on to a more complicated rule. The product rule. A product is 2 things multiplied together. So if we have 2 functions, say h of x is equal to f of x multiplied times g of x. And I want to find the derivative of that. then we can write the derivative h prime as the first function f of x times the derivative of the second function plus the second function g of x times the derivative of the first. So I have first times derivative of the second plus second times derivative of the first. And people say these differently, memorize them different ways. So if you've already got a way that you remember it, that's fine. It's not a problem. This is the standard that we usually use, though. So let's look at a function. Suppose I say my function f prime of x. Let's say if f prime of x is equal to 3x squared e to the x cubed. Well, this is two pieces. There's an x, there's an x. They're multiplied together. So we can think of this as a product. And I have two pieces. I have a 3x squared piece, and I have an e to the x cubed piece. So my first f and my second g, I just have to put in the rule that basically says keep one, multiply, take the derivative of the other and multiply, and then do the opposite. Now, if I take the derivative of the derivative, this is a perfectly good function, I get the second derivative. So what I'm doing is find f double prime of x. So f double prime of x equals first, that's 3x squared, times the derivative of the second. The second is e to the x cubed. Outside function is e to a power. Inside function is x cubed. This is going to require chain rule. E to the u, keep the x cubed, multiplied times the derivative of the exponent, 3x squared. So that's first times derivative of the second, plus second, e to the x cubed, times derivative of the first. I can bring the 2 around front to multiply times the 3, and I get 6x to the first. You can leave it like this. A lot of times, though, because there's an e in both parts, we'll factor out the e part, e to the x cubed. What's left here is 3x squared times 3x squared, when the e comes out, plus this e comes out, and I'm left with 6x. So I have e to the x cubed times the quantity 9x to the fourth plus 6x. Now you could keep going. Math people love to do algebra. You could pull out a 3x, but you may have an answer that stays here. You may have an answer that goes to here. You may have one that continues. It's the algebra that you just have to practice your derivative rules and your problems until you can see how your answer needs to be left. Let's look at another product rule problem. Here we have f of x equal to x minus 3 times x cubed plus 7 to the 5th power. I have two parentheses, so it's pretty evident which is my first and which is my second. So we use the product rule to find this f prime of x. I'll do first, and then I need to take the derivative of the second. An inside function raised to the 5th power. Power rule says 5 comes around front to the 4th power. What's inside does not change. And by the chain rule, we multiply by the derivative of the inside. The derivative of x cubed is 3x squared, and the derivative of 7 is 0. Now, all of that is just first times derivative of the second. And then we have to go plus. We do second, x cubed plus 7 to the 5th times the derivative of the first. Derivative of x is 1. It's the identity function. Minus derivative of 3 is 0. Constant multiplier, constant derivative. So we can clean this up a little bit. I have x minus 3, and I have all of this together. And if you look at the 5 and the 3x squared, I can multiply those because it's 5 times that times 3x squared, which would give me 15x squared. And then x cubed plus 7 to the 4th. And then it's just plus x cubed plus 7 to the 5th. Now, you can't add these together. This part is multiplied by everything up here. And so this is pretty much the simplest form of the answer. I could factor out again here, but that's not necessary. You go to here and you see what happens next. And this is a perfectly good answer. Now we're going to look at some examples of the quotient rule. Of course, not the basic examples, some a little more complicated. The quotient rule, remember, a quotient is a fraction. So if h of x is equal to f of x over g of x, we assume that we have functions of x top and bottom. Then the derivative h prime of x is equal to the bottom, which is g, times derivative of the top, minus the top, f, times derivative of the bottom, all of that divided by the denominator squared. This, because it is subtracted, has to be done in this order. So it has to start off with g and then f prime. Let's look at the function f of t equal to 3t over t to the third minus 5t to the fourth. We want to find f prime. F prime of t equals, we have t's on top, t's on the bottom, we use the quotient rule. Start with the denominator, t to the third minus 5t to the fourth, multiplied by the derivative of the numerator. Well, I have 3, and actually that's supposed to be 3 to the t. I can't read my own writing. That's something you have to watch out for. I had that t kind of close, halfway up. Be careful that you read it correctly, 3 to the t power. The derivative of 3 to the t, I just made it more complicated, didn't I? Exponential function base 3, the rule is natural log of 3 times 3 to the t. Denominator times derivative of the numerator. Minus numerator, that's 3 to the t, times the derivative of the denominator. This is a difference. I just take the derivative of each piece. The derivative of t to the third is 3t squared minus the derivative of 5t to the fourth. The easiest way to think of it, remember, for a constant multiplier, multiply by the 4, 4 5s are 20, decrease the exponent by 1, so it's cubed, all over the denominator squared. T to the third minus 5t to the fourth squared. So let's check this. I started with the denominator times derivative of the numerator, ln of 3 times 3 to the t, minus the numerator times derivative of the denominator over the denominator squared. Now, please notice I have a t to the third minus 5t to the fourth here and here, although it's squared. These do not cancel. You have a subtraction up here. You cannot cancel those two because the subtraction sign divides this into two pieces. Sometimes you may see this 3 to the t factored out of each piece, but this is a perfectly good way to leave the answer for this quotient rule problem. So it's a combination of rules, as a lot of these have been, and we need to think always in terms of if there's an outside and an inside. And the e to the power is one of our basic rules, the e to the u. So let's think of this as e to the u is the outside function, and then we get the derivative of the exponent for our inside function. So f prime of x is equal to e to the power. That part stays exactly the same. Then we have to take the derivative of x times ln x squared plus 1 times, that means product rule. So product rule, product, first times derivative of the second plus second times derivative of the first. The first is just x. So we'll do x times, and when I want to take the derivative of a natural log, the rule for natural log is 1 over u. 1 over everything that's inside here. But then what's inside is not just x. It's not just 1 over x. So I have another derivative to take of the x squared plus 1. Derivative of x squared is 2x. So that was first times derivative of the second, plus, and now I do second times derivative of the first. This is the second, it's just the natural log. The derivative of x is 1. And so that finishes up the product rule for the exponent, which is the inside function. First times derivative of the second plus second times derivative of the first. And you may need to leave it like that. You can do a little cleaning up, combining these terms. So I can write this as e to the x ln x squared plus 1 times this x and the 2x multiply to be in the numerator, 2x squared over x squared plus 1 plus natural log x squared plus 1. And that takes care of everything that we need to do from this function. So be sure to watch out whenever you have functions that have more than just x's, that there's going to be a chain rule. There's an inside function and an outside function in all different combinations, exponential, log, product rule. We've done quotient rule with them also. So be really careful with all the different combinations. And again, you simply have to have all the rules memorized and do lots and lots of practice on your own, getting help, so you're more comfortable with doing all these rules.